Welcome to Physics for Life. This is a quick revision video of chapter Current Electricity. So the study of electric charges in motion is called current electricity. Next is electric current. The flow of electric charges through a conductor constitutes electric current. Quantitatively, electric current across an area held perpendicular to the direction of flow of charge is defined as the amount of charge flowing across that area per unit time. So for a steady flow of charge, I is equals to Q upon T. And if the rate of flow of charge varies with time, then I is equals to limit del T tends to 0, del Q upon del T, which is equals to dQ upon dt. The SI unit of current is ampere. 1 ampere is equals to 1 coulomb upon 1 second. So we can say 1 A is equals to 1 coulomb second inverse. Now next is conventional and electric current. The direction of motion of positive charges is taken as the direction of conventional current, electrons being negatively charged. So the direction of electric current is opposite to that of the conventional current. Now electric current is a scalar quantity. Although we represent current with an arrow, yet it is a scalar quantity. Electric currents do not obey the laws of vector addition. Next is electromotive force. So the EMF of a source may be defined as the work done by the source in taking a unit positive charge from its lower potential terminal to the higher potential terminal, or it is the energy supplied by the source in taking a unit positive charge once around the complete circuit. It is equal to the terminal potential difference measured in open circuit. So EMF is equals to work done upon charge. The SI unit of EMF is volt. If an electrochemical cell supplies energy of 1 joule for the flow of 1 coulomb of charge through the whole circuit, including the cell, then its EMF is said to be 1 volt. Now next is Ohm's law. The current flowing through a conductor is directly proportional to the potential difference across its end, provided the temperature and other physical conditions remains unchanged. So V is proportional to I, V is equals to I R, and V by I is equals to R. And here this R is called the resistance of the conductor. Resistance. So it is the property by the virtue of which a conductor opposes the flow of charge through it. It is equal to the ratio of potential difference applied across the conductor to the current flowing through it, and it depends on the length and area of cross section of the conductor. So R is equals to rho L upon A, and here this rho is the resistivity of the material. Now SI unit of resistance is ohm. The resistance of a conductor is 1 ohm if a current of 1 ampere flows through it on applying a potential difference of 1 volt across its ends. So 1 ohm is equals to 1 volt upon 1 ampere, or we can say that 1 ohm is equals to 1 volt ampere inverse. Now next is specific resistance, resistivity or specific resistance. These are same things. So it is the resistance offered by a unit cube of a material of a conductor. So rho is equals to RA upon L, and its SI unit is ohm meter. So it depends on the nature of material of the conductor and physical conditions like temperature, pressure, etc. Now next is current density. It is the amount of charge flowing per second per unit area normal to the flow of charge. It is a vector quantity having the same direction as that of the motion of positive charge. So for the normal flow of charge, this J vector is equals to Q upon T upon A, which is equals to I upon A. And in general, I is equals to J A cos theta, which is equals to J vector dot A vector. And the SI unit of current density is ampere per meter square. Now next is conductance. It is the reciprocal of resistance. So conductance is equals to 1 upon resistance, and its unit is ohm inverse or mho, or this capital S known as Simon. Now next is conductivity or specific conductance. So it is the reciprocal of resistivity. So conductivity is equals to 1 upon rho. and here rho is resistivity. So SI unit of conductivity is ohm inverse, meter inverse, or mho per meter, or Simon meter inverse. Now next is resistance of different substances. So metals have low resistance in the range of 10 to the power minus 8 ohm meter to 10 to the power 6 ohm meter, and insulators have resistance more than 10 to the power 4 ohm meter, or we can say that their resistance is between 10 to the power 12 ohm meter to 10 to the power 20 ohm meter. And last one, semiconductors ranges from 10 to the power minus 4 ohm meter to 10 to the power 3 ohm meter. And now next topic is color code for carbon resistors. Current carriers. In metals, free electrons are the charge carriers, and in ionized gases, electrons and positively charged ions are the charge carriers. And in an electrolyte, both positive and negative ions are the charge carriers. And in semiconductors like germanium and silicon, conduction is due to the electrons and holes. Hole is a vacant state from which an electron has been removed and acts as a positive charge carrier. Now next is drift velocity and relaxation time. The average velocity acquired by the free electrons of a conductor in the opposite direction of the externally applied electric field is called drift velocity, and it is represented by Vd. So the average time that elapses between two successive collisions of an electron is called the relaxation time, and it is represented as tau. So Vd is equals to minus E capital E tau by m, and R is equals to ml upon ne square tau by a, tau a, and rho is equals to m upon ne square tau, and I is equals to NEA VD, and J vector is equals to N E VD. And here N is number of free electrons per unit volume, or free electron density, and small m is the mass of electron. Now other forms of Ohm's law. So in terms of vector quantities like current density J vector and electric field E vector, Ohm's law may be expressed as J vector is equals to sigma E vector, or E vector is equals to rho J vector. So the equation this E vector is equals to rho J vector leads to another statement of Ohm's law. Uh, a conducting material obeys Ohm's law when the resistivity of a material doesn't depend on the magnitude and direction of the applied electric field. Now next is temperature coefficient of resistance, denoted as alpha. It is defined as the change in resistance per unit original resistance per degree raise in the temperature, and it is given by alpha is equals to R2 minus R1 upon R1 in the bracket T2 minus T1. And if T1 is equals to 0 degree Celsius and T2 is equals to T degree Celsius, then alpha is equals to R1 minus R0 upon R0 into T. Or we can say that R1 is equals to R0 in the bracket 1 plus alpha T. And the unit of alpha is degree Celsius inverse or Kelvin inverse. Now effect of temperature on resistance. For metals a positive, for metals alpha is positive. Uh, the resistance of metals increases with increase in temperature, and for semiconductors and insulators alpha is negative, such as their resistance decreases with increase in temperature. And for alloys like constantan and magnenon, the temperature coefficient of resistance alpha is very small, so they are used to make standard resistors. Now next is mobility of charge carriers. So the mobility of charge carriers is the drift velocity acquired by it in a unit electric field. It is given by mu is equals to Vd upon E, which is equals to Q tau by m, and mu E. This is the of drift mobility of electron. So this is equals to E tau E upon me, and for a hole mu h is equals to E tau h upon mh. and the SI unit of mobility is meter square per volt per second, and practical unit of mobility is centimeter square per volt per second. Now, relationship between I and M. I is electric current, and this mu is mobility. So for a conductor, I is equals to E N A mu E E, and for semiconductors, I is equals to E A E in the bracket N mu E plus P mu H, and rho this sigma is equals to E in the bracket N mu E plus P mu H, where this N and P are the electron and hole densities. Now next is ohmic conductors. The conductors which obey Ohm's law are called ohmic conductors. For these conductors, VI graph is a straight line passing through the origin. For example, metallic conductor for small currents is an ohmic conductor. Non-ohmic conductors. The conductors which do not obey the Ohm's law are called non-ohmic conductors. The non-ohmic situations may be of the following type. First is the straight line VI graph does not pass through the origin. Second is the VI relationship is non-linear. Third, the VI relationship depends on the sign of V for the same absolute value of V. And fourth one is VI relationship is non-unique. Examples of non-ohmic conductors are water, voltmeter, thigh resistor, and a PN junction, etc. Now next is superconductivity. So the phenomenon of complete loss of resistivity by certain metals and alloys when they are cooled below a certain temperature is called superconductivity. The temperature at which a substance undergoes a transition from normal conductor to superconductor in a zero magnitude magnetic field is called the transition or critical temperature, which is denoted by Tc. Now next is Meissner effect. So the expulsion of magnetic flux from a surrounding from a superconducting material when it is cooled to a temperature below the critical temperature in a magnetic field is called Meissner effect. Now next is resistance in series. So when a number of resistors are connected in a series, their equivalent resistance Rs is equal to the sum of the individual resistance. So Rs is equals to R1 plus R2 plus R3 up to Rn. Now next is resistance in parallel. When a number of resistances are connected in parallel, the reciprocal of their equivalent resistance Rp is equal to the sum of reciprocals of the individual resistance. So 1 upon Rp is equals to 1 upon R1 plus 1 upon R2 plus 1 upon R3 up to 1 upon Rn. And for two resistance in parallel, Rp is equals to R1 R2 upon R1 plus R2. Now next is division of current in resistors joined in parallel. So the current is divided in resistors connected in parallel in the inverse ratio of their resistances. So I is equals to R2 upon R1 plus R2 into I, and I2 is equals to R1 upon R2 R1 plus R2 I. And now next is internal resistance denoted by small r. The resistance offered by the electrolyte of a cell to the flow of current between its electrodes is called the internal resistance of the cell. So it depends on the first nature of the electrolyte, second concentration of the electrolyte, third distance between the electrodes, and fourth common area of the electrodes dipped in the electrolyte, and fifth one is temperature of the electrolyte. Now next is relationship between EMF, terminal potential difference, and internal resistance R. So the potential drop across the terminals of a cell when a current is being drawn from it is called its terminal potential difference. It is less than the EMF of the cell in a closed circuit. So E will be equals to V plus IR, and V is equals to E minus IR, and V is equals to IR, which is equals to ER upon R plus small r. So this internal resistance small r is equals to EMF minus terminal potential difference V upon I. which is equals to R in the bracket E minus V upon V, and I is equals to E upon R plus small r, and I maximum is equals to E by R. So the terminal potential difference of a cell when it is being charged is V is equals to E plus I R, or when V is greater than E. This is for charging. And now cells. First is cells in series. If n number of EMF are and internal resistance R each are connected in series, then the current drawn through external resistance R is I is equals to Ne upon R plus Nr. And now cells in parallel. If m number of cells are connected in parallel, then the current drawn through external resistance capital R is I is equals to Me upon Mr plus small r. Now cells in a mixed group. Uh, if n cells are connected in series in each row and m such rows are connected in parallel, then the current drawn through an external resistance capital R is I is equals to Mne upon Mr plus n small r. And for maximum current, the external resistance must be equal to the total internal resistance. So R is equals to Nr upon M, or we can say that Mr is equals to Nr. Now next is heating effect of current. The phenomenon of the production of heat in a resistor by the flow of an electric current through it is called heating effect of current, or Joule heating. So it is an irreversible process. Now next is Joule's law of heating. It states that the amount of heat capital H produced in a resistance is first directly proportional to the square of the current for a given R, and second directly proportional to the resistance capital R for a given I, and third inversely proportional to the resistance R for a given V, and last one fourth is directly proportional to the time small t for which the current flows through the resistor. And mathematically this law can be expressed as capital H is equals to VIT, and its unit is joule, and which is equals to I square RT, which is equals to V square T upon R, or we can say that H is equals to VIT upon 4.18 calorie, which is equals to I square RT upon 4.18 calorie, which is equals to V square T upon 4.18 R calories. Now next is electric power. So it is the rate at which an electric appliance converts electric energy into another form of energy, or it is the rate at which work is done by a source of EMF in maintaining an electric current through a circuit. So electric power, P is equals to W upon T, which is equals to VI equals to I square R equals to V square by R. Now uh, SI unit of power is watt. The power of an appliance is 1 watt if 1 ampere of current flows through it on applying a potential difference of 1 volt across it. So 1 watt is equals to 1 joule upon 1 second, and which is equals to 1 volt into 1 ampere, and 1 kilowatt is equals to 1000 watt. Now next is electric energy. It is the total work done in maintaining an electric current in an electric circuit for a given time. So electric energy is equals to electric power into time. So W is equals to PT, which is equals to VIT joule, and which is equals to I square RT joule. Now units of electric energy. The commercial unit of electric energy is kilowatt hour, or broad of trade BOT unit. It is the electric energy consumed by an appliance of power 1000 watt in 1 hour. So 1 kilowatt hour is equals to 1000 watt hour, which is equals to 1000 watt into 3600 second, which is equals to 3.6 into 10 to the power 6 joule. And another unit of electric energy is watt hour. So 1 watt hour is equals to 1 watt into 1 hour, which is equals to 3.6 into 10 to the power 3 joule. Now next is power rating. So the power rating of an electrical appliance is the electrical energy consumed per second by the appliance when connected across the marked voltage of the mains. So P is equals to V square by R, which is equals to I square R, which is equals to VI. Now next is power consumed by a series combination of appliances. So this is the formula. The reciprocal of the effective power is equal to the sum of the reciprocals of the individual powers of the appliances which have been manufactured for working on the same voltage. So 1 by P is equals to 1 by P1 plus 1 by P2 plus 1 by P3 up to 1 by Pn. Now power consumed by a parallel combination of appliances. The effective power is equal to the sum of the powers of the individual appliances. So P is equals to P1 plus P2 plus P3 and up to Pn. Next is efficiency of a source of EMF. So it is the ratio of output power to the input power. If a source of EMF E and internal resistance small r is connected to an external resistance, then its efficiency will be this eta will be equals to output power upon input power. So which will be equals to Vi upon Ei, which is equals to V by E, which is equals to R upon R plus small r. Now maximum power theorem. It states that the output power of a source of EMF is maximum when the external resistance in the circuit is equal to the internal resistance of the circuit. When capital R will be equals to small r. So maximum power will be equals to E square by 4R. The efficiency of a source of EMF is 50% when it delivers maximum power. Now next is efficiency of an electric device. So it is a ratio of the output power to the input power. So it is equals to output power upon input power. First, for an electric motor, eta is equals to output mechanical power upon input electric power. And second, input electric power is equals to output mechanical power plus power lost as heat. So the power output of an electric motor is the maximum when its back EMF is half the source of EMF, provided the resistance of the windings of the motor is negligible. Now next is Kirchhoff's law. These laws enables us to determine the currents and voltages in different parts of the electrical circuits. So here the first law, it is known as junction rule. In an electric circuit, the algebraic sum of the currents at any junction is 0, or the sum of the currents entering a junction is equal to the sum of the currents leaving that junction. Mathematically, summation of I is equals to 0. And justification, this law is based on the law of conservation of charge. When the currents in a circuit are steady, charges cannot accumulate or originate at any point of the circuit. And here the second law, it is also known as loop rule. So around any loop of a network, the sum of the charges and potential must be 0, or algebraic sum of the EMFs in any loop of the circuit is equal to the sum of the products of the currents and resistances in it. So summation del V is equals to 0, or we can say that summation E will be equal to summation IR. So justification for this law is this law is based on the law of conservation of energy. As the electrostatic force is a conservative force, the total work done by it along any closed path must be 0. Next is galvanometer. So it is a sensitive device to detect current in a circuit. It produces a deflection proportional to the electric current flowing through it. Next is potentiometer. It is the device used to compare the EMFs of two sources. Its working is based on the principle that when a constant current flows through a wire of uniform cross-sectional area and composition, the potential difference across any length of the wire is directly proportional to that length. So V is proportional to L, or we can say that V is equals to KL, where this K is the potential drop per unit length, which is called the potential gradient. And potentiometer have mainly two uses. First is this use to compare the EMFs of two cells. So if K1 and K2 are the L1 and L2 are the balancing lengths of the potentiometer uh, for cells of EMF E1 and E2 respectively, then E2 upon E1 is equals to L2 upon L1. And second use is to find the internal resistance small r of a cell, and its formula is R is equals to E minus V upon V into R, which is equals to L1 minus L2 upon L2 into R. Now next is Wheatstone bridge. It is an arrangement of four resistances P, Q, R and S joined to form a quadrilateral ABCD with a battery between A and C and a sensitive galvanometer between B and D. The resistances are so adjusted that no current flow through the galvanometer. The bridge is then said to be balanced. In the balanced condition, P by Q is equals to R by S. Knowing any three resistors out of these four, the fourth resistance can be computed. A Wheatstone bridge is the most sensitive when resistances in its four arms are of the same order. And the now last topic is slide wire bridge or meter bridge. It is an application of Wheatstone bridge in which R is fixed and a balance point is obtained by varying P and Q, such as by adjusting the position of a jockey on a 100 centimeter long resistance wire stretched between two terminals. If the balance point are obtained at the length L, then P by Q is equals to R by S, which is equals to L upon 100 minus L. Or we can say that S will be equals to 100 minus L upon L, this all in the bracket into R. So resistivity rho is equals to SA upon L, which is equals to S into pi R square upon L. Thank you for watching the video.